you. Right, so here's my presentation. And it's use and abuse of phase diagrams. And I'm from Wits University. And I've put it into three parts. One, a little bit about phase diagrams, then using phase diagrams, and then abusing phase diagrams. So this could be 101, except that it's very elementary, so I've called it 000. So why are phase diagrams important? Well, they show us what phases are present and their proportions. And because phases define the properties, that helps us define which applications we can use them for. Most alloys are actually made from more than two components. And so it's important that we understand not only two-component phase diagrams, but what we call higher order, which is three or more. Ternary is three. And why are phase diagrams so important? We often find we have to combine new data with what is already known. And that helps us, having decent phase diagrams, helps us if you're doing research on alloys, trying to make new alloys and trying to improve alloys. So first of all, what is a phase? It's got a distinctive temperature range and composition range, and it's also got a distinctive structure. I've shown close-packed hexagonal, otherwise known as hexagonal close-packed. And when you look at the micro, hang on. When you look at the microstructures, you will see nice interfaces between phases. So here we've got three phases, a light, a medium, and the dark, and we call those interfaces. And then we've got boundaries between the same phases. And here are some of the common structures. There's loads more, but these are the ones that are common because they've got, especially for metals, because they've got decent properties. You can see phase diagrams as maps. But as with all maps, you need to know how to use them. So here's our first director. I'm taking the photograph, totally lost in a Japanese railway station. And here's my old cycling group, totally lost, even though they've got the map and there's a signpost there. So you've got to know how to use them. And usually for alloys, as a metallurgist, because that's what I am, we are only interested in solid phase and the liquid phases just above the melting point. So what we do is, unlike geology, we assume that the pressure is atmospheric. And what that does, it reduces a degree of freedom here. So these I define, reduces that degree of freedom, and it makes things simpler. My geology friends laugh at me, and here's a paper by some geologists. They were looking over this temperature range here, and what they're plotting is volumes of different cells. And you can see there's a very much difference as you change pressure. And that's just to put that in to say, I know in my work I'm cheating by making it more simple, but that's what we're interested in. Whereas if you look at what the geologists are up to, they're interested in very high pressures because they're trying to work out what's happening deeper in the earth, even as far as the earth's core. So phase diagrams are all about stability. If you define delta G as the change in free energy due to a reaction, and that can be a new phase, you can say if that delta G is negative, the new phase is thermodynamically stable, it will exist. If it's zero, the new phase is thermodynamically metastable, and if it's greater than zero, it's not stable, so it's unstable. You can either do that across the whole system, or you can look at this for separate phases. So here, because the liquid is lower, it's the most stable phase at that particular temperature. So there's various phase diagrams, and I just put some examples here. Different sorts because of various different things, various different energies, lattice structures. Taking a common type phase diagram, this is aluminium silicon, more of that later, and basically we've got the liquidus, which is usually the first line we're interested in. And remember, as a metallurgist, a physical metallurgist, I'm only interested in the liquid just above that, not anything higher. And then so beneath the liquidus, everything is liquid. Above, sorry, it's start again. Above the liquidus, everything is liquid. Below the solidus, that's this orangey, supposed to be red, everything is solid. And between the two, you've got a mixture of liquid and solid. And you can see them drawn over there much nicer. And despite the fact I said we're not interested in anything higher, I just put this in for fun, and you've got the gaseous phase. Very important phase diagram is iron carbon, and there's actually two forms of that, more of that later. And we have various common reactions, liquid plus a phase already forming, going to form another phase. That's a peritectic. A eutectic, where you have a liquid going to form two different phases. And then a eutectoid looks very much like the liquid, but you've got a solid phase up here. So the nice thing about iron and carbon is that iron has got two different structures. This structure and that structure is actually the same, and then another one there. And as soon as you have that happening, you have quite complex phase diagrams, and you can do a lot of interesting things with them. This shows that there's two different versions of it. And what happens is at lower temperatures, this eutectoid is more likely to be this phase, alpha ferrite, and cementite, which is iron carbon, because the atoms have to diffuse smaller distance, or can only diffuse smaller distances. So therefore, it's easier to have cementite, this thing, rather than pure iron. Okay, so the phase diagram, once you know how to use it, can give you a hint for that. And then this I pinched, I use it in teaching. There's the eutectic, it's at higher temperatures. There's the eutectoid at lower temperatures. This is the sort of diffusion distances from there to there that you've got at liquid. And if you look in here, you can just see some lines, and that's what's happening in that reaction, the eutectoid. And this, once you understand this, this will actually help you interpret that microstructure. All good fun. So phase diagrams help you recognize microstructures and find out what's going on there. So here you've got some various microstructures. And looking at this one, this is the first phase to form because it's a dendrite. And it had all the freedom to form, and metals like to form dendrites. This is a secondary dendrite, not a peritectic, that formed on that. And then finally you get a eutectic, and that formed first. Okay, so you could use this interpretation to work out what on earth was going on in the phase diagrams. And what we were doing in this piece of work, we were actually trying to interpret the phase diagram, and then we were helping the development or the explanation of nickel-based superalloys. We were going to make it more complicated than this, but there were some things which needed sorting out first. So here's a dendrite which formed first. Then you got a peritectic reaction here, and you form those needles. And then lastly, you got a eutectic. And if you make loads of alloys, you can go back and check the phase diagrams. One thing you can have, and I've got this here in a binary phase diagram, Masowski is a really good reference for binary phase diagrams, even though it's quite old. It's a good starting point. And here you've got 1, 2, 3, 4, 5 peritectic reactions. And what happens here, it's called a cascade because the liquid can run down and nothing can stop it. And you can get some really horrible things happening on fast cooling. Another thing you can do with phase diagrams is if you know the composition, which is we're taking the composition as X, you can work out the phase proportions. So for liquid, we're in the two-phase region at this temperature. Basically, it's that line over the whole line. For B, it's hypothetical. It's that line over that line, and you could put in the actual numbers, but I think it's easier to draw the lines. Then most things, as I mentioned earlier, are more than two elements. They're often more than three. I chose this not because it's particularly useful to me, but it's nice and clear. But unfortunately, most people would look at that and think, oh, don't know what to do with that, run away. But that is the whole picture of what's going on in this particular phase diagram, hafnium, boron, carbon. But people don't like that. So what we do is we take bits out of it. You can either have a liquidous surface projection where it's like you're looking down on it, and there's an example, and that can be really useful and give you things, good information. Or you can take an isothermal section, so same temperature. That's really useful because what you get there is phases that are in equilibrium. And this has got various names: vertical section, isopleth, there's a few others. There it is being cut through there. It can be cut anywhere. Normally it goes from one of the corners to another phase, and there's an example there. I don't particularly like these. They're not that useful, but unfortunately, people like them because they think it makes the phase diagram easier to read because they're taking it back to binaries. But I'll explain why that's not that useful. So these are things that people use to try and get away from this three-dimensional space diagram. The liquidous surface is very useful. The isothermal section is very useful, but the vertical section is a bit misleading. So what does the liquidous surface tell you if you've got one? Well, on these, if you're on one of these surfaces that's bounded by lines, you know that this phase forms first. If you're on there, this phase forms first. This is a modelled one because it's in the CalFad journal, more of that later. And they haven't put arrows on this, so I put some of them on. And between two liquidous surfaces for different phases, you have a univariant line. And where you have three of them mixing, you've got an invariant reaction. It goes back to that phase rule, okay? And these green lines are isotherms. They're at the same temperature. So this is very useful because if I plotted a composition on there, I could work out how it solidifies. Very nice and useful. And once you know what's happening, you can also pick out some of the invariant reactions from the shape. So you've got a ternary eutectic there, a ternary eutectic there, and a weak ternary peritectic there. And you might think, well, what are they? Don't worry, I'm going to tell you. So here's another one, and this hasn't got the isotherms on, but it's fine. But it does have some arrows on, and it's been redrawn a different way because we're only really interested in iron tungsten. We're not interested in carbon because after here, all you get is graphite forming and it's boring. And this is a sort of truncated triangle. This is not a rectangle here. And it will just go on until that line and that line come together. So this is nice because we've got a weak ternary peritectic, 2 arrows in, 1 out, a strong ternary peritectic, 1 arrow in and 2 out, and a ternary eutectic reaction, 3 arrows in, more of that. And here we are explaining that. So ternary eutectic, it's liquid going to 3 different phases, solid phases. A weak ternary peritectic. It's like a mixture of a peritectic, because the liquid is reacting with something, and a eutectic, because you're forming two things. And then a strong ternary peritectic, the liquid reacts with alpha and beta to go to gamma. Okay, and some people like to call these things class 1, class 2, class 3, and I've put that in for completeness. And then I've got some examples of these taken from various work. So here's our primary phase. Don't worry about what we call these. Here's our primary phase. They're pretty ropey dendrites. So that's, if you like, generic liquid going to alpha. Now we've got a binary eutectic forming, liquid to alpha plus beta, those two phases. And then over here, you'll see there's 3 phases in there. That's a ternary eutectic, liquid going to alpha plus beta plus gamma. And there you are in there. Quite good fun, that. Here is and that was a class 1 ternary eutectic. Here's a class 2, and it's a weak ternary peritectic. This is the primary phase, and there's something weird going in there from what you know already, because where we looked at things in the binaries, you don't have the same phase as this very light phase in there. So therefore, there's been an invariant reaction that liquid reacted with this. You can see a bit of a fuzzy outline there to form that eutectic growing off. So that's a weak ternary peritectic, or class 2. And then this one is a class 3, or a strong ternary peritectic. So first of all, you had the primary dendrites forming. Then you had a eutectic, and you can see one of the phases in there is the same as there. So it's the same as in the dendrites. And then what happened is the liquid reacted with this to form this last phase, gamma. So that's class 3, or strong ternary peritectic. This I cheated. I'm sorry, I didn't put where I got it from, but this is a nice liquidous surface. It's got the isotherms labeled. It's got arrows on the univariant reactions. The liquid surfaces are labeled. We know that's a maximum because the arrows, which always go in the direction of decreasing temperature, are going away from each other. And then a hatched part shows 2 liquids. Sometimes, especially when you've got more complex things, you can have not 1 liquid, but 2 liquids. So that makes it kind of interesting. And then from here, you can work out how it's going to solidify. So if that's the composition of this, because we're on this liquidous surface, it's going to form that. And because that has got no range in compositions, as that solidifies, the liquid composition will move directly away from it, over that liquidous surface, until it reaches this univariant line, which happens to be a eutectic because it's got a nice V. It'll run down there, and then it will run down and form the ternary eutectic. So you could plot any composition on there and work out exactly how it will form. So it's really nice and useful. Then there is computer calculation of phase diagrams, the CAL and the FAD. And there's many commercial programs of this. The one we use is Thermocalc. There's also some others. And most of them use the same databases with the information, which was started to be gleaned from experimental results. And there's also some ab initio results in there as well. And there are also some specialized databases, like for titanium, for hard metals, and for geology, actually, and oxides. They are more expensive. So here's a calculation on Thermocalc. That's their little symbol. And this is for the aluminium chromium system. And this shows you what phases are in equilibrium on the boundaries, and then you've got some reactions there. And hey, you've got one of those cascades of peritectic reactions. Then if you've got something that's got more than 3 things in it, so it's not a ternary, so this is titanium, molybdenum, ruthenium, and copper. So what you can use, I call it a phase proportion diagram because that's what they show. Thermocount calls it a property diagram, which I think is a stupid name. Well, it's not a phase diagram, but it is showing you what phases are present at various temperatures. So at high temperatures, you've got liquid. As you cool down, the liquid solidifies, and you start to form the body-centered A2 phase. And then you have all body-centered A2 phase. Then you start to have titanium to copper coming out, and then you have the HCP phase coming out, and that's directly related to that. It's a transformation. So that's nice. It's not a phase diagram, really useful for when you've got more than 3 components. This is a calculated isothermal section of chromium, platinum, ruthenium. You'll see why we got into that. And we've put the experimental points on. Some of them are quite good, some of them less good. There was a reason for that. And then this was an extrapolation from the 3 binaries, because if you've got a ternary diagram, you've got the 3 binaries on each edge. So this is an extrapolation from that and seeing what you've got. It wasn't too bad. These are where you've got 3 phases in equilibrium. Where you've got the green lines, those are 2 phases of equilibrium. There, the program bombed out. And then this is a single phase region of FCC. And then this is quite fun. This is also a binary extrapolation. And it's got a whole bunch of phases marked on. And what I want to compare it with, and if I put it on the same slide, you couldn't read what was there. So this is the experimental version, okay? And they actually are quite similar. The only thing that's really different is that you've got 2 ternary phases in there, and there may be another one there, which there was no way you could calculate because you've got to have some data in there to calculate it. So what you would normally do in a situation like this, and we were doing it, is you get some experimental data, then you'd plug it back into the program and you'd refine this and you get better and better. So it's quite good. Right, using phase diagrams. And it's frozen on me. So here we've got, this was my first contract at Mintech. They were very interested in this stuff, aluminium ruthenium, or you can call it ruthenium aluminium, because it's high melting point, it's related to body-centered cubic, and it's got very good properties. And they were eventually using it as the electrode in spark plug. But when they tried to make it, they got something horrible that looked like this. So there's your ruthenium aluminium. There's another phase, which is there. Then you've got this phase, which is, no, you've missed out that one. Then you've got that phase, but you've got a whole load of peritectic reactions as you go down here, and you're getting that. So if they'd understood the phase diagram, they said the phase diagram was wrong. So we got master's project out of it, and this is Tracy's work. We weren't sure of exactly where these boundaries were, so we did them dotted, which is a bit naughty. We should have said, no, this is where they are. But because they didn't understand how this worked, they thought it was wrong. There's a couple of other phases that we put in there as well. So you want to avoid that. This phase diagram will tell you that on solidification, you're going to get a mess like that. So what you do is if you wanted solid aluminium ruthenium, you'd probably have to use mechanical alloying and then anneal it up there, and then you get a really nice thing. Coring is where you have a wide gap between your liquidus and your solidus, And what happens, the liquid runs down there, the solid runs down there, you get these rings forming, and you get variations of composition as it solidifies. Now, it's great if you want a teaching slide, but it's not great if you want to do something useful with that, because this will have different properties from that slightly, and that could be enough to mess it up. And also, if you want to put that in a corrosive environment, corrosion loves differences, and one of these will eventually corrode before the others. So how to get rid of that? Either have a different system which doesn't have such a big gap, or you could know that you've got to cool this slowly to allow equilibrium to happen, or heat treat it at a high temperature so there's good diffusion, and you miss off some of these mess. Okay, and then here's aluminium silicon, very good for alloy wheels. There's a few other things put in there. If you cast this thing, say about, we're over on this side, you're going to get big needles of silicon, okay? And silicon is brittle, and what can happen, it can crack very easy, it can jump across a little neck, carry on cracking, jump across a little neck, carry on cracking, jump across a little neck, and soon this whole thing has got a crack running through it. You really don't want that. So what they can do two things. They can either hold it at temperature, in which case you get a structure more like that, because holding at temperature below the melting point, below the eutectic, this has now got high energy because it's got high surface energy. So the system, the metal itself, will want to reduce that surface energy and will round off these silicon needles to make globules, and that gives you much better properties. This is the old solder. It's still really good. People have been trying to get rid of it for ages because of lead, and lead is poisonous, okay? The only problem with this is that it's difficult because it's cheap and it's also low temperature. People have and you want a eutectic, because if you have it here where there's no range of solidification temperatures, it's got good flowability. Or over here, because you're in a two-phase region, liquid and solid, we call it pasty, and you can bend the joint. So the electricians liked it here to flow into the joint, but the plumbers liked it here so that you could bend the joint to the right shape. So a lot of people have been doing a lot of work to get rid of lead because of it's a health hazard. Right, then tungsten, cobalt, hard metals. This is a calculated isothermal section, drawn a bit differently, but it doesn't matter. And what you want to be in here, you want to be in this region. This is basically liquid cobalt, and it's in equilibrium at 1400 degrees Celsius with tungsten carbide, which is your strong phase, and cobalt is the binder and gives it some gives it a bit of ductility. If you come off that, either way, you will not be in a two-phase region, and over here you'll pick up carbon, which you don't want because it makes it more brittle, and over here you pick up the eta phase, which you don't want because it makes it more brittle. You want to be in here, but the problem is you want quite a high proportion of tungsten carbide, and you'll see as you move towards it, this phase field gets more narrow, and so it's more difficult to stay in it and maybe wander in and get some sigma, some eta phase rather. So you want to avoid that. What people do now, this is it's a section, calculated section through the system, and it's got tungsten, carbide, cobalt, and nickel, okay? And this is the sintering window without nickel. Okay, this is the sintering window with nickel, and you can see it's a little bit wider, so that gives you a bit of help, but it's not exact because the tie lines do not lie in the plane of the section, but it's better than nothing. This was us playing. This was quite good because this is working with quite a big group in the States, and it's platinum enhanced radio opaque stainless steel. And what they wanted to do is we wanted, because this was one of my bits of it, we wanted to put platinum in there so that it was easy to see under X-rays when they put the stint in the right position. But the problem is you do not want this phase, which is the ferrite, because it's magnetic. So you wanted to reduce that. So we played around with how much platinum that you can put in. That's got no platinum in it, and that's got 10% platinum in it, and we've brought it down. And there was a certain limit we had to bring it down. And interestingly enough, this has now gone commercial. And I think it took about 10 years, which is a record. And then sometimes you've got what we call a higher order system, but sometimes you can get away with using a lower order system. Here's a binary, and basically both of these are in there. You've got dendrites of platinum, and then you've got a eutectic and a eutectoid, which is this mess in here, which has become 2. And you can get away with using the binary as a guide if you've got small amounts of other things in there. This was quite good as well. Again, we've got the same old binary, and you'll see why we were looking at these. Got the same old binary in there, and that is dotted because they weren't sure about it. If you put ruthenium in there, then it helps stabilize it. And what you can see is the eutectic reaction there, and you can also see the eutectoid reaction there. That was the dendrite, which has now decomposed. So these were beta dendrites, which have now decomposed. So that was quite fun. Right, why were we doing this? Basically, this is an old project, but it's fun. Everything is about getting cheaper and greener and trying not to mess up the environment. If you've got a turbine engine and you have it hotter, it's more effective, you can go faster, and it also uses up less fuel. So this is where it's really, really hot in here. So you need alloys that can withstand high temperatures and also not corrode, because the fuel itself is pretty corroded. Now this is an old slide. I admit that, but I haven't come across a slide that shows it nicely. So basically what they're doing is going through more and more then advanced aeroplanes and engines, and this was the kilograms of carbon dioxide, okay? And they weren't sure about that at the time. And that was over a Tokyo to Sapporo journey, which is equivalent to Joburg to Cape Town. And this is why, this is for nickel-based superalloys. As you've got different alloys and as you treat them better, so this is wrought. Now you've got conventionally cast, so you've brought down the grain boundaries, then directly solidified, you've brought them down even more. Then single crystals, you've got no grain boundaries, and because the grain boundaries slide against each other under stress at high temperatures, basically, if you get rid of them, if you reduce them and get rid of them, you get better properties. So creep is where you hang a big weight on something, and then you see how long, and you test it under a certain pressure, okay? So that's the weight on it, and then that's the hours, and you see how long it extends it. And if it, and that's the test. Again, an old slide, but it shows it nicely. Then to get beyond that, what you do is you put a thermal barrier coating, and that helps insulate it. So that's really good as well. So modern nickel-based superalloys, you've got precipitate in there, which is harder and stronger, and then you've got the nickel-based solid solution, which is softer, and you can have some carbides, and that gives you really good properties. But what's happening is you're constrained by these temperatures up there. Maybe you can get them to go higher. And this is a very popular alloy. It's still being used, CMSX4. This is one of those diagrams to show you what's happening. You've got gamma prime precipitates coming out, and you've got the bit of gamma, which is the FCC, the dark bit. If you run it for too long, you get these horrible brittle phases coming out. So nickel-based superalloys are really good. The only problem is you would like to get really higher. What about ceramics? Well, they can be brittle. People have been working and are still working on molybdenum boron silicon alloys, and they're getting better properties now. We tried, because we lived in South Africa, with a nice consortium, because South Africa's got platinum, with Japan, Germany. That's why a lot of the slides came from Japan. With Germany, UK, and South Africa, we tried to make that, but with our platinum-based alloys. That's an early stage. That's quite nice. These are later stages. So we got there. And this just tells us why we use platinum, high melting points, and that's our project, which ran there. Actually, it ran a little bit longer than that. And very nice project. It was fun. Right, but there's problems, because here you've got that phase there, and there's no other, there's no other phases within it. Over here, you've got at least 2 phases in there, so that's a problem. Okay, so but you can stabilize it by putting things into it like chromium and ruthenium. Then there's 2 versions of the platinum aluminium phase diagram, and one has got 2 phases at lower temperatures. The other has got just 1 phase down here, lower temperature phase, but it's at much higher temperatures. And this is actually an impurity effect, because part of our group got this and part of our group got that. And this had purer materials. That's cubes, which is really nice. And here you can see the atoms are in, this is 2 different, slightly different versions of that. The atoms are in slightly different positions. You don't want that, but you can stabilize that. And this is what they look like under the transmission electron microscopes. If you've got the more complex structures, you get these laths, so the properties aren't so good. So we've said one of our good alloys. One of ours was that. The Germans didn't like ruthenium, so they put in nickel. Then we were playing around with the database. Could we, using our database, I've shown some of the results of that. Could we actually predict this? Because we were going to take this further and further. And then we put niobium in. The reason we put niobium in, it's to improve precipitation strengthening. It does improve the creep strength, and also it makes the alloy cheaper and a little bit light, well, cheaper definitely, and a little bit lighter by replacing some of the platinum, so that's good. So, excuse me, so we did some more work on that. We've got reasonable properties. That's the sort of region we're interested in, and that's the sort of region we're interested in. We went wider because it's fun. There's some more stuff. Pretty nasty system there, so that's a bit worrying, because you could get other precipitates coming out, which these are all brittle as anything. That was fun. And then vanadium. Vanadium is great because it actually increases the melting point of that platinum solid solution. But you've got these nasties lower down, so you'll have to avoid that. And that just shows, again, that's the region of interest. So that's our gamma prime, that's our gamma. there's our region of interest there. Kind of interesting. Not sure. Oh, that just shows some various other work we did. We have to go quite far over there, but this doesn't give us our cubic precipitate. There's some more fun things we did. So now we have an alloy which looks the same as our nickel base, not ours, the commercial nickel base superalloys. But platinum group metals are dense and you want lightweight in aeroplanes, they're expensive. So that's why we did the substitution. You could make simpler coatings with platinum aluminium, and there are the competition I've mentioned. Gamma titanium aluminium people like, but it's only for low temperatures. So there is a niche for very corrosive environments in at high temperatures, and missiles and space use, which probably won't be recycled. Now abuse, I realise I'm running out of time a bit. Beware of different versions, use the right one. Materials Science International, which I do some work with, they've got a Eureka platform, and what we do there is we look at various versions that have been published in the phase diagrams, and we assess which is the best one, okay? And we choose that, and we say why we think the others aren't so good. And it could be not necessarily newer is better, but you can have more samples, different techniques with agreement between the techniques, different modeling. Some modeling is better than others. Did they anneal it for longer? So then you get more equilibrium. Better techniques they use, preventing unwanted reactions, different purities of components. We do things like that. Now, this is titanium aluminium, and you can see this one is different from that one, which is different from that one, and there's some differences here. So this was the one we picked, but that was through going all the data. And then so the abuse would be using the wrong one, especially when there's a better one that's around. This is they call it a pseudo-binary, but it's really a sort of shorthand for the different phases. And people use this as a phase diagram, and they shouldn't. I've seen it done, and basically it's just to show you where certain alloys, these are all commercial alloys, fit in between the beta phase, the alpha phase, and there's a martensite phase in there, depending on how you call it. So don't use that as a phase diagram, it's just a guide. And then this unfortunately has got my name on it. And if this is a section going through a ternary, which is copper, gold, and aluminium, and that just shows you how you get section. And if you can imagine drawing a straight line anywhere, these are two different systems, but if you draw a straight line, you're never going to get the tie lines all lying in that section. So the only thing you can really rely on this is that liquidus line. The rest of it, the phases will be the same, but the compositions won't be the same. But people love these things. And I say that's got my name on it, because they make things, they think it makes it easier. So that's me. Sorry I went on a bit long, but here's thanks to the students and my collaborators who did phase diagram work. I hope I didn't leave off anybody. And this is the various places we got funding from during the course of the work. And there's quite a few different things there. And that's me. Thank you.
Thank you, Lesley.
We still got some people left. So I did get a bit carried away, I'm sorry. But yeah, if there's any questions, I'll be happy to answer them. Lesley silence. Yeah, please go ahead.
Yeah, thanks, Prof, for the presentation. Yeah, I just have got a quick question. for me, it's why do you think in other institutions like research institutions, they are not using phase diagrams more often? For example, is it because they are relying more on mechanical testing, or is there a link between the use of phase diagrams to to mechanical testing other than composition? I just want clarity on that, because it's a good
So,
thing to,
yeah,
yeah, like,
that's a good, sorry. Yeah, that's a good question. If you know the material very well, like where you are, because the material's been around a long time, you don't necessarily have to get involved with phase diagrams, okay? Because you know the material well. You know what you're going to get, okay?
oh, okay.
And I know where you are, you have had people looking at phase diagrams. But if you know the material that well, you don't have to bother with the material, with phase diagrams, because you know it, okay? But if you're trying to either develop new alloys or trying to work out why you get failures in alloys, or not necessarily failures, but especially when you're trying to make them and you're not getting what you think you should, then it's worthwhile looking at phase diagrams.
Oh, okay. So, like, if I'm changing the manufacturing method, it's also useful to look at phase diagram.
Yeah, but for your particular material, you probably don't have to, because it's sort of fairly, it's pretty well known.
Oh, okay.
For everyone else, I happen to know this because Andrew's my student.
Oh, okay.
So
All right.
I'm not psychic. But yeah, so you wouldn't have to get too worried with phase diagrams. But when that material was in an earlier stage, there was a lot of phase diagram work.
Okay, all right, thank you.
Hey, are there any more questions? Hey, if there's not, I'd like to say thank you to everyone who attended and close the meeting. Unless you've got something to say, Sandra, or something to push me to say.